Hi students, welcome to lecture 5, which is about the sun. I want to spend a moment talking about why the sun is important. The sun is at the center of our solar system, as you know from previous lectures. And the sun is by far the largest object in our solar system. In fact, the vast majority of the mass of the solar system is in the sun. So this implies that the sun is probably very important in the history of our solar system, in the way that the solar system behaves and the properties that it has, which is true. There are also some other reasons to study the sun. The sun, as you probably already know, heats the surface of the Earth and its atmosphere. And it's vital to the vast majority of life on Earth. We depend indirectly or directly on plant life, and plant life depends on the sun. But there's another reason to study the sun which maybe you haven't thought of. This is maybe the purest astronomical reason, and that is that we want to study stars in general. When you look out into the universe, you see a lot of things, but many of the things you see are stars. And certainly if you look at the night sky, that's generally what you see. You might see the moon, some planets, but generally speaking, you see stars. And so therefore it's natural for us to want to understand stars if we're interested in astronomy. And the sun is a star. But the sun is a special star in the sense that it's very close to us. We don't think the sun is special in any other way, which is actually very helpful in terms of understanding other stars, because we can study the sun up close, and therefore whatever we learn about the sun we hope is applicable to other stars in the universe. And therefore, from our perspective as people interested in astronomy, the sun gives us an opportunity to study up close a star. We can actually send craft to the sun or near the sun. We don't send the craft in the sun, but we can plant spacecraft near the sun, and we can collect data to try to understand what's inside the sun and the surface properties, etc. And we cannot do this for any other star in the universe. Remember that even the closest stars to us, other than the sun, are very far away. They're so far away it would take many thousands of years for human craft to get there with our current technology, and therefore we don't have this opportunity with any other star in the universe. Let's first talk about the structure of the sun. The sun is a giant ball of gas. It does have some other stuff in it. We'll get to the composition of the sun a little bit later in this lecture, but it's almost completely gaseous, and or at least the elements in the sun are gas, gases. And at the core of this sphere, we have what we call the core, as you might imagine. And the core is an extremely hot, dense place where we have fusion taking place. The sun is very hot and very luminous. It emits tons of light because of the fusion reactions that are occurring in the core of the sun. We will get to what fusion is later in this lecture. For now, I will just say that fusion is the process by which stars generate light and heat, thermal energy. Above the core, we have the radiation zone. Above that, we have the convection zone. I'm just going to circle these so you know where in the diagram I'm looking. And then we have what we refer to as the surface of the sun, the photosphere. The sun is gaseous, and so therefore it doesn't have a surface the way that a terrestrial planet like Earth has a surface. If you fall toward Earth, you will know when you hit the surface. The Earth also has an atmosphere, and so it's a bit more complicated because if you're going really fast, you'll burn up in the atmosphere first, as most rocks do that hit the Earth. But let's take the example of Mercury, for example. Mercury is the first terrestrial planet. It has basically no atmosphere. If you fall toward Mercury, you will hit a rocky surface at a very particular point in time that you will be able to determine when it occurs. But the sun is not like that because the sun is gaseous. And so when I talk about the atmosphere of the sun, I'm using the term in a somewhat more abstract way. We're still talking about gases here, but we refer to the photosphere roughly as the surface of the sun. And the reason we do so is because this basically is the place from which the light that we observe from the sun is emitted. It comes from the photosphere. Above the photosphere, we have the chromosphere, and then above that, above that we have the corona. Let's first talk about the atmosphere of the sun. I'm including, by the way, the photosphere in the atmosphere of the sun. We refer to this, remember, as the quote-unquote surface, but since the sun is gaseous, the atmosphere and the surface are sort of interchangeable. So the first part of the atmosphere is what we refer to as the surface, which is the photosphere. This is about 500 kilometers thick, and it has a temperature of about 5,800 Kelvin. When we refer to as the surface temperature of the sun, this is what we mean. We refer to the photosphere, or the temperature of this photosphere. Then we have the chromosphere, which is right above the photosphere. This is a transparent and much larger layer. It's about 10,000 kilometers thick. And its temperature is actually higher than that of the photosphere. Finally, we have the corona. This is an extremely wispy, very thin, amorphous layer that is millions of kilometers thick. It's above the chromosphere, and its temperature is actually even higher than the chromosphere. It's around 1,000,000 degrees Kelvin. This is rather a mystery, by the way. You might think that this is very puzzling because, for instance, Earth's atmosphere doesn't behave like this. The surface of the Earth is hotter than the upper atmosphere. The upper atmosphere of the Earth is very cool. And this is generally true of atmospheres, and therefore you might wonder where this effect comes from. Well, this is a bit of a mystery, but perhaps I'll talk about this a little bit later in the lecture. Let's talk about some of the things that happen in the atmosphere and some of the structures in the sun's atmosphere. I mentioned in a previous lecture that the sun has a very powerful magnetic field, and it's also a variable magnetic field, meaning it's always changing. When you think of a magnetic field, you should think of loops. The field will form loops. These loops can be very complicated and interwoven, and these loops are always changing. They're moving around and they're breaking and they're reconnecting. And a lot of the mechanisms that are responsible for the ejection of gas from the surface of the sun, for example, we think are related to these highly variable magnetic fields. There are jets of gas that are emitted called spicules. And in general, this very active surface of the sun that's always emitting gases and ionized particles creates what we call the solar wind. This is a general term we have for the emission of particles from the sun. This is generally what we refer to it as when it's in the solar system, meaning outside of the immediate vicinity of the sun. So for example, the solar wind passes by Earth. And this is a thin stream of ionized particles, meaning charged particles, that passes past the planets away from the sun at very high speeds, around 350 kilometers per second, sometimes even higher. And this, we believe, can be responsible for stripping away the atmospheres of planets. I talked about this a little bit when we discussed Mars versus the Earth. We haven't done a lecture on Mars yet, but I talked a little bit about the planet, but we'll have a whole lecture just on Mars. And I did mention to you that the Earth has a magnetosphere. It has a magnetic field. And this magnetic field, we believe, protects, there's strong evidence that it protects the atmosphere of Earth from the solar wind. The solar wind would otherwise pass by Earth at a very fast speed. It's a thin stream, but over millions and millions of years, this can strip away, and does strip away the atmosphere of planets. but our magnetic field actually captures these charged particles and forces them into the poles. And therefore, our atmosphere is not being stripped by these particles because they're not passing by Earth unabated. Let's talk about the spectrum of the atmosphere. I talked about spectroscopy in an earlier lecture, particularly when I discussed light and also when I discussed the atom. Just a very quick review. An atom is an object that consists of a nucleus and then electrons surrounding the nucleus. And we are made of atoms, or more specifically, atoms make up molecules and we're made up of molecules. And the sun is made up of atoms. The elements, hydrogen, helium, oxygen, carbon, I'm reading from the elements here. I'll get to this table in just a second. But these elements, all elements, are made up of atoms. And atoms have some special properties. Try to think back to the lecture where I discussed atoms. If you don't recall that lecture, please go back and watch the lecture on light and telescopes, where I talk about light and how light is emitted and absorbed by atoms. But just to give a very quick review, an atom consists of a nucleus, which is here in blue, and then electrons which orbit around the nucleus. In order for an electron to go from the lowest state, which we call the ground state, which is this circle in black, to the first excited state, which is this one in red, the electron has to absorb a very specific amount of energy. You cannot push the electron to a state that's in between these two. That's what's special about an atom. This picture of an atom might look like a little solar system, but it's not, because when a planet orbits a star, that planet can, in principle, be pushed closer to or farther away from the star. But an electron cannot be pushed arbitrarily close to or away from the nucleus. It's either in the ground state, or it's in the next state. We call that the first excited state, or the next one, etc., etc. There's nothing in between the states. So you cannot take this electron and push it to this state here, because there's nothing in between the solid black orbit and the solid red orbit. Just erase this here. And this gives rise to what we call a spectrum. An atom has a spectrum. This is the list of wavelengths, in other words, energies, because wavelength can be related to energy, the list of wavelengths of light that can be emitted or absorbed by an atom. An atom can only absorb or emit wavelengths of light that correspond to shifts in these energy levels, going from one orbit to another. And because there's a finite number of orbits, there's a countable number. There's not an infinite number. It's just one of a handful of orbits that you can move to or away from if you're an electron in an atom. This means that an emission spectrum will look like this. It will look like a black tape, so to speak, with specific colors that are filled in. I'm just drawing random colors here. This doesn't look like a particular spectrum, but these specific colors are going to be the specific wavelengths of light that correspond to correspond to differences in the energy levels of the atom. And the point here is that this acts like a chemical fingerprint, because every atom has a unique spectrum. Therefore, this gives rise to what we call spectroscopy, which is the study of spectra. We can study atomic spectra, the spectra of atoms, and then we can compare atomic spectra to the spectrum of the sun. You can study the light that comes from the sun. You can collect it, all different kinds of light, and then you can categorize it. How much light comes in the form of yellow visible light versus UV light versus blue visible light versus X-rays, etc. And what you will find is that you get a very wide variety of wavelengths that come from the sun, but very specific wavelengths will be cut out. So remember I mentioned emission spectra. This is the kind of spectrum you get from an atom, or let's say a bunch of atoms. If you have hydrogen gas, for example, that you heat up, the kind of spectrum that you get is an emission spectrum, which I was just talking about. The sun gives us a different kind, sort of the opposite kind. You can think of it like that. We call this an absorption spectrum. This looks like the full range of colors, and of course that only corresponds to visible light, but the full range of the electromagnetic spectrum with very specific wavelengths that are cut out. And these wavelengths that are cut out we refer to as spectral lines. These are dark lines, and they will correspond to wavelengths of light that can be emitted or absorbed by specific atoms. I've done a poor job highlighting them because I've covered the names of the elements, but these two are for hydrogen and helium. This one is for sodium, and this one is for iron. This is for mercury, etc. I've covered it up again. I want to point out that atoms have multiple absorption lines. So for example, you can't point to this one here and say, well, this one is sodium. It is a sodium absorption line, but sodium has many. What you'd have to do, for example, therefore, is look at all of the absorption lines here, and there's many, obviously, and then you'd have to compare these absorption lines to the lines that we have from chemistry experiments. You would take atoms, or chemists would take atoms in the laboratory and find what their spectral lines are. So you call up your chemistry friends and you ask them for the spectral lines of hydrogen, let's say, and then you find those lines in the spectrum of the sun. This is known as spectroscopy, the study of spectra. In particular, we're talking about stellar spectroscopy. And using this method, we can determine what is in the sun and in what proportions. The long and the short of it is that the sun is made up of almost entirely gas, hydrogen and helium gas, but it has trace elements of other stuff: oxygen, carbon, nitrogen, even things like silicon, magnesium, neon, iron, sulfur. You might wonder where the iron in the sun comes from. No one went to the sun and dumped a bunch of iron in there. That's a very interesting question, and I won't give you the answer, but I will say that we will talk about this when we get to how stars die. That's actually the answer to the question of where the iron in the sun comes from. When we talk about the evolution of stars and what happens when stars begin to die, then the answer to this will become clear. You can tell that I'm spending a lot of time on this subject, spectroscopy, and that's because it's a particularly important subject. For one, it is a really good example of how we can take terrestrial physics, in other words, a study of atoms that we find, that we find on Earth. And we can do experiments with these atoms on Earth, etc., and how we can apply this to distant stars. Let's talk about the sun's interior again. Let's go back to the interior. I mentioned to you that the interior has several parts. One is the core. That's how I started. This is where nuclear fusion occurs. I'll get to nuclear fusion a bit later. Then we have the radiation zone. The radiation zone is the part of the sun. I just want to go back to this picture here. It's the part of the sun where energy is transported primarily through radiation. That means that light is propagating through the radiation zone, and the light is carrying energy. And this is how energy is propagated through the radiation zone, and that's why we call it the radiation zone. The convection zone is the zone above the radiation zone, and it's called the convection zone because energy is transported here primarily through convection. Convection, remember, is, I mentioned to you that it's important, is the process by which hot gases rise and cool gases fall. Therefore, we have circulating gases in the convection zone that are transferring thermal energy, the energy of the vibrations of molecules to the outer layers. So in everyday language, we would say the heat of the sun is transported through the convection zone by circulating gases. Let's talk about the rotation of the sun and the core of the sun a little bit. There's many amazing facts to relay here, but one of the amazing facts is that the core has a tremendous density. Its density is about 150 times that of water, and it has a temperature of about 15 million degrees Kelvin. The sun actually rotates, but because the sun is not rocky, it's gaseous, different parts can rotate at different rates. And in fact, that's exactly what happens. The equator actually rotates faster than the poles, rotates about once every 25 days. And near the poles, we have a rotation once every about 35 days. Let's talk about one of the very important concepts that relates to the stability of the sun. I mentioned to you that I didn't tell you exactly how much, but I mentioned to you that an enormous amount of energy is released in the core. The sun is very hot. The core is extremely dense and extremely hot, and of course, the surface is thousands of degrees Kelvin. And so therefore, you may expect that the energy center of the sun, which is in the core, is releasing huge amounts of energy. In fact, we have fusion reactions occurring in the core of the sun, and fusion is the process by which thermonuclear weapons work. Therefore, there's a natural question to ask, which is, how come the sun doesn't explode? What's causing the sun to be stable? After all, the sun doesn't increase in radius tremendously and then decrease in radius. It's not oscillating back and forth. It's actually a very stable object. And the answer to that question is that the sun is in hydrostatic equilibrium. This will become a very important topic or concept, particularly when we get to how stars die. Hydrostatic equilibrium means that there's a balance of forces. Gravity is the force that is pulling the sun inwards. The sun has a tremendous mass, so it has a much larger gravitational pull than does Earth. And the force that's balancing gravity, which is pulling in, is a force that's pushing out. And that force comes from the fusion that is occurring in the core of the star. There's a huge amount of energy released in the core of the sun, which is pushing the star outward. And this, we believe, is a general principle of stars, not just of the sun. We can determine, by the way, that gases move up and down inside the sun by studying the Doppler shifts of spectral lines of the sun. We talked about the Doppler shift in a previous lecture. The Doppler shift is the increase or decrease in the wavelength of light, depending on whether the source of that light is coming toward you or away from you. If I shine a flashlight in your direction, and then I move away from you, suppose I'm facing you, but I'm turning the flashlight toward you so you can see it, but I go away from you at a tremendous speed, the light from your perspective will look much redder than it does from my perspective. I might think that the light is white. It's a white or let's say yellow light, whatever. But you might think that the light coming from my flashlight is a deep red because the wavelengths of light that are emitted by the flashlight are getting stretched out. Correspondingly, if I move very quickly toward you with a light, then the light will get what we call blue shifted, which means that it will look bluer to you than it does to me. This is the same principle by which we can determine that there are gases that move up and down in the sun. This is actually a very nice diagram from your book which depicts this process. We have gases here which are moving up and down inside the sun. When these gases reach the surface of the sun, they will emit light that we can see. The light that we see from the sun is really being emitted by the surface. And we can then study the Doppler shifts of the spectral lines. Remember we talked about spectral lines? Another use of spectral lines is that by studying whether they're shifted to the high wavelengths or low wavelengths, you can determine the Doppler shifts. Or I should say, that is the Doppler shift, when a spectral line that's supposed to be at, let's say, 432 nanometers, corresponding to some atom, is actually shifted toward the higher end or lower end of the wavelength spectrum. Okay, so this is it for hydrostatic equilibrium. Try to put this in the back of your mind for when we get to the part of the course when we talk about stars evolving over time and dying. Then this will become very important. I want to show you some pictures of the interior of the sun, just to emphasize what I was saying earlier. This is a really nice diagram from your book that emphasizes that in the radiation zone here, light is transported via, energy is transported via light. Light propagates through this zone. And then in the convection zone here, we have energy that is transported via convection. If we look at just under the surface of the sun here, what we will find is that we have convection cells just below the surface, and this produces what we call granulations. So we say that the sun's surface is granulated. This occurs because we have hot gases moving up and cool gases moving down, and this creates what looks like some kind of structure, which we call granulations on the surface of the sun. Let's talk about the sun's surface in a little bit more detail. The sun's surface has small, cool patches that are known as sunspots. These look black, but they're not really black. If something is black, such as the vacuum of space, what it means is that it's not emitting light, or it's an object that's absorbing light, which means it's not emitting light. For example, a black hole is black because it absorbs all the light that comes near it, and it doesn't emit any light, or hardly any light. And this principle applies to the surface of the sun, but this principle is relative. So the black spots that we call sunspots on the sun's surface still emit light, but because they're much cooler than the surrounding area, they emit a lot less light, and therefore they look black. These sunspots are typically about the size of Earth, and we don't know why sunspots form, but we think that it has something to do with magnetic fields, because the magnetic field in and near these sunspots is much larger than the magnetic field on average near the sun. In fact, it's larger by about a factor of 100. The sun goes through cycles. You may have heard of sun cycles. These cycles relate to the activity on the surface of the sun, and in particular, in regards to sunspots, there are more or less sunspots over roughly 11-year cycles. So every 11 years or so, you have a maximum amount of sunspots, and then when you're in the other part of the cycle, the number of sunspots is a minimum. However, these cycles are not set in stone, because they can last between 7 and 15 years, but on average they're about 11 years. And sunspots positively correlate with solar activity. That means that if you are in a part of the cycle where there's a lot of sunspots, the sun will be very active. Remember, the surface of the sun is a very active place. Gases are moving up and down, and gases are falling back down in coronal rain, so we call coronal rain, and gases are being emitted, huge masses are being emitted in the form of gas and charged particles from the sun all the time, and this happens more frequently when we have more sunspots. Here's an example of a sunspot. There's a real picture here. So remember, these places on the sun are still hot, they're still emitting light, they're just much cooler than the surrounding areas, and so therefore they look black. Let's finally talk about nuclear fusion, as I promised earlier in this lecture. Nuclear fusion is what powers the sun. And nuclear fusion is the process by which particles are forced together, they're fused together, and when they fuse, they produce other particles, and this releases tremendous amounts of energy in the form of light, as well as in other forms, other particles. This, as I said earlier, is the process by which thermonuclear weapons function. And so as you can imagine, this releases tremendous amounts of energy. It does so because energy and mass are two forms of the same thing. This is a famous idea that comes from Einstein, E equals mc squared. This was derived by Albert Einstein when he came up with his special theory of relativity. We don't have time to talk about all of that, but the idea is that even a little bit of mass has a lot of energy. So if you can take, let's say, two protons and force them together, you can produce, and let's say you do that with two other protons, you can produce a helium atom. And in the process, you release a small amount of that mass in the form of energy. That energy can be in the form of light. It can be in the form of what we call positrons, which are just some kind of exotic particles, or neutrinos, which are even more exotic particles. And this is what's happening in the core of the sun. This picture, by the way, I just wanted to include because it's a beautiful picture and it depicts a coronal mass ejection. This, I guess I should have moved closer to the structure of the sun's surface and the stuff that's happening on the sun's surface. But I was talking about earlier about how the sun is a very active place, particularly the surface. So this is an example of how active the surface of the sun is. This is an ejection of a huge amount of gas from the surface. The rest of this lecture is going to mostly consist of videos that I want you to watch on your own. I'm going to post links to these videos on Blackboard. I won't actually show them in this video, but it's important that you watch them because they're part of the lecture. Before I get to those videos, I want to talk about some of the details that I've glossed over in this video. One of them is why the corona is so hot. I mentioned earlier that it's a bit of a mystery why the corona, the outer part of the sun's atmosphere, is much hotter than the chromosphere, which is above the surface, or the surface itself, the photosphere. And this is something that's rather hard to explain, but there are a number of explanations which people advocate for and also critique. One of them is that waves carry this energy to the corona. Another proposal is that this energy is released via the breaking and reconnection of magnetic fields. Remember I talked about how the sun has many highly variable magnetic fields, and when these break and reconnect, this releases tons of energy. I want to talk about two missions to the sun. These are called SOHO and TRACE. I want you to watch this video to learn about these two missions and how these missions give us tons of valuable information about the surface of the sun, but also what's happening inside the sun. But I'll leave it to you to watch the video. And then I want you to watch this video on solar flares by the NASA Goddard Center. Solar flare, I should say, to back up, refers to the emission of charged particles from the sun, and it's a particularly large emission. That's generally what we refer to as a solar flare. And these solar flares can pass by Earth, and of course we have a magnetic field that protects us, but nonetheless, sometimes solar flares can be so intense that they can actually knock out satellites, etc. So I want you to watch this video on solar flares. The last thing I want to talk about are neutrinos. Remember I mentioned that nuclear fusion produces light, but also some exotic particles such as neutrinos and others. I would like you to watch this video on neutrinos that is about IceCube. IceCube is a very large experiment taking place in the South Pole, or near the South Pole, in Antarctica. And the experiment actually uses a massive chunk of Arctic ice that's just naturally there to study these little particles called neutrinos. Neutrinos are particles that are so tiny that they mostly pass through the Earth. Whatever neutrinos come toward the Earth generally pass straight through the Earth. That's how small these particles are. The sun is emitting gargantuan amounts of neutrinos every second. Billions and billions of neutrinos are passing through your body every second. At night, when you go to sleep, you should think about this if you have trouble sleeping. Neutrinos are being emitted from the sun toward the earth, but through the other side of the earth, because when it's midnight, the earth is blocking the sun, right? That's why you can't see the sun at night. So the sun is actually on the other side of the earth. The neutrinos being emitted by the sun are passing through the other side of the earth, through the entire earth, up through the floor, through you, and then out into space. Let's talk about what neutrinos are a little bit. These are really tiny particles that are about a millionth as massive as the electron. I mentioned that they're produced in massive quantities in the sun. In fact, you can compute roughly how many are produced, and you can actually calculate there's about 65 billion neutrinos passing through every square centimeter on the Earth night and day. A square centimeter is roughly the area of your fingertip. And these particles mostly pass straight through Earth, but occasionally one of these neutrinos will interact with some atom or molecule on the Earth, let's say ice in the South Pole, and ice cube can then detect these particles by detecting these interactions. Neutrinos will slam into the ice sometimes, and then this releases light as well as a whole shower of other particles, and by reconstructing these collisions, we can determine that there are neutrinos impacting the ice and where they're impacting and what the energy was. So IceCube studies neutrinos via this method. And this slide is really a bit of an extra slide that I just wanted to include just to show you the how neutrinos can be produced. It doesn't so much matter what the details are, but this is a particular particle interaction that produces most of the neutrinos that we have in the sun, that are produced by the sun, rather. The neutrino is this particle here. That's the symbol we use for it. So this slide doesn't matter so much. If you're interested in learning more about this, you can go to this link. But otherwise, you don't have to know this particle interaction. But you should know these basic facts about neutrinos. And once again, please make sure to watch these videos. I will post all 3 of them. Yes, there's 3 on Blackboard. Thank you very much for watching this lecture. Just to recap, this is lecture 5. This was on the sun. The sun is a massive ball of gas. It's also a star. And the things that we have learned about the sun, we hope to be able to apply to other stars in the universe. Soon we're going to get to studying the parts of our universe that are outside of our solar system. That includes other stars. And then we will apply this knowledge, such as hydrostatic equilibrium and stellar spectroscopy, etc., to those stars. Thank you for watching, and I will see you in another video.